We're going to demonstrate the in-system debugging capabilities of Atmel Studio with a simple example project. The hardware used is the SAM3N EK board and the SAMICE debugger. For the project, we have chosen the Getting Started SAM3N EK. This demonstration program makes two LEDs on the board blink at a fixed rate, using interrupts from a timer counter. AVR customers may be familiar with the AVR simulator. To debug code for an ARM processor in Atmel Studio, it will be necessary to use the SAMICE. Once connected, this will by default become the selected debugger programmer. The supported interface is JTAG. Click on this button to bring up the Select Debug Tool window. If you have more than one debugger connected to your computer, you will be able to select which one to debug with in the Select Debug Tool window. Close the window. You will now see the SAMICE with serial number in brackets selected as the default in the Device and Debugger toolbar. Before we start debugging, let's add a variable to watch. We would like to look at the section of code which turns the LEDs on and off. Let's add a variable called counter to count the number of times the LED is toggled. Make this volatile so that it doesn't get optimized away by the compiler. To start debugging, click the Start Debugging and Break button. This will stop program execution at the first line of main. A Seger J-Link control panel window will pop up. Minimize it. Now, a stopped status is displayed in the lower left corner of Studio, and a yellow arrow indicates our position in the code. When debugging, the output window at the bottom of the screen is replaced by a debug-specific collection of windows, like the breakpoints and watch windows. The Solution Explorer also gets replaced by the Processor tab, which shows the state of key registers including the program counter, the stack pointer, and the status register. A cycle counter is also available. You can also look at the I/O view, which shows the state of all the peripherals registers. This can be opened from Debug Windows I/O View. Let's set a breakpoint on the GPIO toggle pin LED0 GPIO function. Right-click on it and select Breakpoint, Insert Breakpoint. Click Continue, and the processor will execute the program code until it halts at this breakpoint. Add the variable counter to the watch window by right-clicking on the variable and selecting Add Watch. We can now see the counter and its value in the watch window. We can now step into this function by clicking on the Step Into button, or by pressing F11. Go to the I/O view, select Parallel Input-Output Controller, PIOA. PIO toggle pin uses an if statement to check DW pin, i.e. pin 23 of the PIO ODSR, the Output Data Status Register. Clicking on PIO ODSR, we can see this is a read-write register. We can see that pin 23 is a logic 1, so the next statement will be processed and a 1 will be written to a write-only register, PIO CODR, the Clear Output Data Register. This is confirmed as we step over this line. The P23 changes from a solid block to being outlined in red instead, indicating that it changed from a 1 to a 0. Our LED turns on. Now, here's a really neat feature. We can actually control the LED directly by clicking on a register. But first we need to write a 1 to the relevant OWER, Output Write Enable register. Entering FFs will enable writing to all the port pins. Now we can control I/O directly via the ODSR. Clicking on PA23 in the PIO ODSR will toggle its value between 0 and 1, turning our LED on and off. Click Step Out to return from this function. Click Run a few times. The breakpoint will be hit each time, and you will notice the variable count in the watch window being incremented. Click Reset to reset the processor. Click Stop to terminate the debug session. For more detailed information on Studio debugging, see the Studio Help chapter on debugging.